Okay, let's use this vertex form a little bit. In example 1a, to graph a parabola, in vertex form. Let's graph the function f of x equals 2 times x minus 1 squared plus 3. And the first thing that we should think about when we are getting ready to graph this parabola in vertex form is where our vertex is going to be. Well, let's think transformations for a second. Normally, our parent function, our vertex, is at 0, 0. This minus 1 is going to move our graph to the right one. And then we have our vertical stretch, and then we move our graph up 3. So our vertex is at the point 1, 3. And again, you can also see that based on our equation, our h value, and then our k value. And be careful, I guess, that the sign goes with. It's plus 3, so our y value is a positive 3. And then our vertex form is x minus h. We have x minus 1 here. These signs are the same. H is just this number right here. So our vertex is 1, 3. All right. Now, when we graphed our transformations of our parabolas before, we made our table for the parent function and then changed all of our x and y values accordingly. I'm going to show you guys another little trick that we can use. In order to graph our parabolas. So the first step that we will do is to plot the vertex. And our vertex is 1, 3 again. And we plotted our vertex. And remember that your parabola is the same on both sides. After we plot our vertex, we're also going to draw in the axis of symmetry. And this is nice to have just because it's a visual for us that our parabola should be the same on both sides. Again, we could make our table for the parent function and adjust all of our values accordingly, but here's another thing that we could do. We could pick an x value on one side of our vertex. So we could pick x equals 2. So this is x equals 1 here, x equals 2 here, when our x value is 2. When we figure out when our x value is 2, wherever that point is going to be the same on the other side of our axis of symmetry because our parabolas are symmetrical. So that's step. Again, x equals 2 is probably an easy value to plug in. So look at our equation. We'll take 2 times, we want x to be 2, 2 minus 1 squared plus 3. Let's figure out what this is. So 2 minus 1 is 1. 1 squared is still 1. Times 2 is 2. plus 3 is 5. So the point 2, 5, is also on our parabola. And since we have our point here, it's the same on the other side of our axis of symmetry. We'd have 0, 5. And repeat the process one more time. Remember, we like to have 5 points total. We like to have our vertex and then 2 on each side. We could also use 3 as an x value. So let's repeat our process. 2 times 3 minus 1 squared plus 3. 3 minus 1 is 2. 2 squared is 4. Times 2 is 8. Plus 3 is 11. So 3, 11 is also on our graph. So this is 5. And again, we're same on the other side of our axis of symmetry. So follow that across over here. Connect our dots. And we have our nice little graph. So one other thing that I'm going to write in here, again, was our axis of symmetry. Our axis of symmetry, a vertical line, so it's x equals. And anywhere on this line, our x value is 1. So our axis of symmetry is x equals 1. But that's a nice, easy way for us to graph. One other thing that I want to talk about, it's been a little while since we've talked domain and range, so let's come back to it again. Domain, if you remember, that's all of our possible x values that we can have on a graph. So looking how far to the left does our graph go, how far to the right. Keep in mind these arrows are really important. So this arrow means we're going to keep going up forever, but we're also going to go to the left forever. Same thing on the right side. This arrow means we're going to go up forever, but also to the right. We go to the left, we go to the right. Our domain is all real numbers. And then range, that's where we are looking at the possible y values on our function. How far up, how far down does our graph go? Well, we're going to go up forever because of these arrows. The farthest down we go is to 3. So all of our y values are above 3. Y is greater than or equal to 3 is our range.